So now let's try to apply the technical lemma we saw from last time. So let's just consider a representation of a compact group, so a unitary representation of a compact group G. What we do is we pick a non-zero vector that's called a U, and let's form a rank 1 operator, basically the projection onto the range of U. Let's just assume the U is a unitary vector, so things are nice. So let's assume U, the length is equal to 1, so the UU star is basically this operator. So I should say B times another vector V is essentially just you take the inner product of this V with the U, so that's the U star part, and then you map it to U, okay? So this is the rank 1 projection onto the linear span of this U. So if you let B to be this rank 1 operator, so that's clearly inside B of H pi, and you construct the operator A from the technical lemma we saw from last time, so you integrate this B, but you conjugate pi x and pi x inverse on either side. So here the H1 and H2 are basically both the H pi, and your pi 1, pi 2 are the same. But in any case, what you end up with this A from last time, you see that this A should be inside the C of pi, so it's an intertwiner of this pi to pi. And moreover, we can actually show the following. So this A is in fact very nice, and that is going to be positive, so it's a positive operator. Second of all, it's going to be non-zero, so you're not integrating something that's non-trivial, something that's trivial. And finally, this A is in fact a compact operator. Okay, so that's going to be really useful. So let's prove these facts. So this A inside the C of pi really just follows from the last lemma. We saw it from last time, so there's nothing to prove here. And let's just show that the A is positive. So why is positive? Well, if we consider what happens to A times some vectors, say U and U, okay, so that's just essentially just the integral of the, well, when you take the integral, and because the integral is linear, you can move the U and U inside. So this is essentially just whatever you're integrating, this operator, pi x, B pi x inverse, and then you inner product U with U, and then you have the dx, okay? So what is this? Well, I should probably give another letter because I already have a U here, so let's change it to V here. Okay, so what happens to this B is that, well, this B is basically the operator UU star, so I have the pi x UU star, and then I have the pi x inverse, which is, you can think about it as a pi x star times V. And then let's just move this pi x to the other side. So you have another copy of the pi x star of V, okay? And you treat this as a vector. So the UU star, when you apply to this vector, basically you take the inner product. So this is the pi x star V inner product with U. And then you left with another vector U, okay? So that's what happens in the first one. And then you do this inner product with the pi x star of V, okay? And what happens is, well, in the first coordinate, your inner product is linear, so you can move this out. So this is pi x star V U, and then the inner product, you multiply the inner product in the other way, so pi x star V. But because your inner product is Hermitian, this is just essentially equals to the integral of the absolute value of this inner product, okay? So you have pi x star V with U, the absolute value squared dx. And because now you see it's an integral of something that's strictly positive, well, something that's positive, so this is going to be non-negative, okay? So in particular, your A, this AV inner product with V is always going to be non-negative, so A is a positive operator. And to show it's actually non-zero, well, we evaluate at the U. So if you evaluate AU with U, so what happens is you do the same calculation. This is just equals to the integral of what happens is you basically replace all the V by U, so you have a pi x star of U and U, and then whole thing dx. I want to show this is strictly positive. Well, why is that? Well, because when at x equals to the identity, your pi x is just equals to the identity operator. So you're integrating this function, this pi x star uu. This function, if you treat it as a continuous function from g to the real, well, this is going to be strictly positive near the identity, okay, near x equals to the identity. Because it's strictly positive and is continuous in x, so this is going to be strictly positive, okay? So in particular, your A is not going to be the zero operator. And finally, we need to show that this A is a compact operator, okay? So the idea is quite simple. You kind of use some finite dimensional approximation of this A. So what you do is the following. So if you think about your function, let's say the function x going to the pi x of u, okay? So this is a continuous function from g to the h pi. And so g here is compact. So you know the continuity will imply the uniform continuity. So this is also uniform continuous. So being uniform continuous just means, well, you can kind of use a finite number of points to approximate your function, okay? So basically for every epsilon greater than 0, you can check this implies that you can partition G into a disjoint union of these EI, going from 1 to n, EI, and they're going to be disjoint. And on each of this EI, you can approximate the pi xu by some pi of fixed point, say pi xi of u. Okay, so you have some xi, and let's say there exists an xi inside each of these EI, so that whenever you want to evaluate pi x u minus pi xi of u, that's going to be less than epsilon, let's say, over 2 for all x inside this EI, okay? So basically on each of these partition EI, the value is approximated by this pi xi of u. And you can only do this when your G is compact, of course. But once you do that, you consider the following. So you kind of do the operator A we had before is the integral of these B, this rank 1 operator conjugate on two sides. But now you do another version, you do a kind of a discrete version, you replace these integral by a kind of a sum. So you let A epsilon to be the following, you let A epsilon to be the summation of I going from 1 to n, and on each of these EI, you multiply the Haar measure, mu is the Haar measure, and then you do the pi of the xi, and then you times the b times the pi of the xi inverse, all right? So this is clearly going to be a, basically b here is a rank 1 operator, so you conjugate two things that's still rank 1, and then you time a scalar, and then you do a finite sum. So this is a finite rank operator, okay? So this is finite rank because it's just a linear combination of a bunch of one-dimensional projections. But if you think about what happens when the difference between this A epsilon and A, well, this A epsilon, first of all, you can write it as the following. So you can write it as the summation I going from 1 to n. It's essentially just a discrete version of the A. So on each of these EI, you use the constant pi x multiplied by this B and pi xi inverse dx. Okay, you're basically integrating this constant. All right, so basically now you want to compare with A. So your A is really the summation I come from one of the integral EI. Well, it's just the integral over the entire thing, but let's just break it down into each of these EI. So you have a pi x b pi of x inverse dx. So the first question you ask is, well, what's their difference? So if you, now let's just briefly look at what happens to these two operators, so what exactly they are. Well, if you think about this operator, let's say pi of x times the uu star of the pi x inverse, and then if you want to evaluate at a point v, well, what it does is basically, we already seen this, this is pi x times the uu star applied to this factor, pi x star v, and then essentially this is equals to the u star will make a scalar, so this is pi x star v inner product with u, so that's a scalar multiplied by u, and you apply this to pi x, so you end up with pi x u here. All right. So another way you can move the pi x star to the other side, so this is essentially v times inner product with pi x u, and then you have a pi x u again. Well, this is essentially this rank 1 operator from the pi x u star. Okay, so you see this is essentially you inner product with this vector pi x u, and then you move it to pi x u this vector. Okay, so this is the rank 1 operator like that. And so if you consider now I have the difference between the pi x b and pi x inverse, and then minus pi of xi b pi of xi inverse. Well, what it does is essentially this is the difference of two rank 1 projection. Okay, so this is the pi x u times the pi x u star minus the other rank 1 projection, basically replace the x by xi, so xi u pi of the xi u, the whole thing star. And you do the standard triangle inequality, you write it as you break it down into two kind of one dimension, these rank 1 operator. So first of all, you say, well, this is pi x u minus pi of xi u, the whole thing, you use the pi of x u whole thing star. So this is the one that inner product with the pi x u, and then you move it to the range of this factor. But you do the other way, okay? So you have the pi of xi u, and then you have the pi x u minus pi of xi u, this whole thing star, okay, the norm of that. So you break the norm as these two rank 1 operator. The nice thing about the rank 1 operator is that their norm is essentially just the product of these two vectors. Okay, so you think about uv star, this rank 1 operator, the norm is essentially just equals to the u and times v. Okay, so this is going to be equals to the following. So you have a pi x u times the difference of pi x u minus pi of xi u, and then you sum the other one, so pi of xi u times the difference between these two. Well, the difference we know because of this uniform continuity and our choice of this EI, they are going to be less than epsilon over 2. And pi is always a unitary representation, so pi x u is just the length of this vector, and let's just assume u is a unit vector, so this length is equal to 1. So this whole thing is less than epsilon. Okay, so we see that on each of these EI, where these pi x, either you conjugate it by pi x or you conjugate it by this pi of xi, they only differ by epsilon as well. So what you end up with is that if you consider the norm of a minus this a epsilon, okay, so this is going to be equals to on these going to be the summation and I going from 1 to n of each of these EI, you integrate the difference. Okay, you integrate the difference between I should say less than or equal to pi of x b pi of x inverse minus pi of xi b pi of xi inverse, right? And each of these absolute value, well, this operator is less than or equal to epsilon, and if we normalize the g so that the left Hart measure is equal to 1, then, well, you just integrate. So each one of these is essentially just equals to the mu of EI times the epsilon, less than that. And you sum them up, it's going to be less than epsilon. Okay, the summation of mu is EI is just mu of g, which we can always normalize it to 1. Okay, so they're less than epsilon. But in any case, we have the a epsilon is converging to a in norm. Okay, so in norm. And each of these a epsilon is finite dimensional or finite rank. So by definition, your a is going to be compact. Okay, so that's how you get the compact operator a. Well, as an immediate corollary, what we have is the following. So if you have a irreducible representation, so let's think about what happens when pi is irreducible. So let's say pi from g to b of h pi is irreducible, and g is compact. Then what happens is you construct the same A, well, you get something that's non-zero and is compact and is in the intertwiner. Well, but the Schur's lemma tells you, well, if you're already starting with the irreducible one, well, there's not many things in your intertwiner, okay? So the only thing happens is the constant, okay? The constant times the identity operator. Well, it just means your A has to be some multiple of the identity, but it's going to be compact. Well, so it just means the compact operator is the identity operator is compact. Well, that just means your space has to be finite dimensional. Okay, so in other words, this h pi is finite dimensional. Okay. Okay, so the proof is just like what I said. Okay, so from the previous lemma, so from the previous construction, we have that this A is inside C of pi, and A is compact, and A is non-zero. So the Schur's lemma tells you, because you have a irreducible one, this A is equal to some constants of the identity, C is non-zero, so the identity is compact as well. So the h pi is finite dimensional. Okay, so that's what we have. And moreover, I can actually also show the following. So let's do the following theorem. So in fact, this also shows that every unitary representation can have a direct summand of these irreducible ones. So every unitary representation, let's say pi of a compact group G, is going to be a direct sum of irreducible ones. Okay, and not only is a direct sum of irreducible ones, we know each of these irreducible ones are also finite dimensional. Okay, so it's a direct sum of finite dimensional unitary representations. All right, so to prove this, we need something operator theory. I'm not going to talk about it. The idea is the following. So if you construct the same A as before, okay, construct A as before, and you have this A is non-zero and A is compact, we need a little bit more operator theory about these compact operators. You're going to learn this again in Pure Math A10 when we talk about operator algebra. But the thing is, the compact operator, their spectral theory is very nice. Okay, these A are not only compact, they're also self-adjoint. Okay, they're positive. A is positive. So what happens is that the spectrum corresponds to its eigenspace. Okay, so A can be kind of, you can diagonalize this A. Okay, the idea is that each of these eigenspace, you can decompose this h pi using these eigenspace. So in particular, there exists one. Okay, so there exists a some non-zero eigenvalue. So that if you consider as eigenspace M lambda, the eigenspace, these eigenspace is finite dimensional. And if you think about what happens to this eigenspace, so in fact, so for every psi inside this space, basically A psi is just equal to some lambda times psi, all right? So that's the eigenspace. But if you think about what happens when you apply pi to it, okay, so you apply a pi x to that. Well, because A is an intertwiner, so you can move the pi to the left and you apply A to the side first. But the A psi is just by its eigen, so it's a lambda psi, and you have a pi x. But now you move the lambda to the left-hand side, so it's lambda times the pi x psi. So what you show is that A applied to this vector is, well, also lambda times this vector, so this is still an eigenvector, okay? So basically you have that pi x psi is still inside the M of lambda. Okay, so in other words, your M of lambda is invariant under pi. Okay, so it's invariant for pi. So in other words, you can always have a finite dimensional invariant subspace. And if you just look at, if you restrict your pi to this m lambda, well, that's going to be a finite dimensional representations. Well, because your dimension is finite, that's going to be a direct sum of irreducible ones. Okay, so that's going to be a direct sum of some pi lambda I. Okay, so each of these lambda I is going to be irreducible. Okay, so in other words, every non-zero, non-trivial unitary representation, you can kind of pull out some part of it that's going to be a direct sum of a bunch of irreducibles one. Well, now you just use a Zorn's lemma. Okay, so now you use a Zorn's lemma argument. So you do the maximal ones. So if the maximal ones is not, then the rest of it you can still do the same trick. You pull out another summand of a bunch of irreducible ones. So basically, your maximal direct sum of these irreducible representations has to be pi. Okay, so pi has to be equals to the direct sum of some pi I, where each of these pi I is irreducible. Okay, so this basically finishes the proof. Okay, so now we can see that the representations, the unitary representations of compact group, they're always a direct sum of these irreducible ones. And the irreducible ones, they're also finite dimensional. Okay, so that's the nice thing about compact. So you can compare this with the example I showed in the last video, where you have a non-compact, even though it's a billion. Well, then in the left regular representation, even though it's not irreducible, it's not going to be a direct sum. Okay, so that's the difference between compact and non-compact.